right. Hi guys. This is first time I ever do something like this, so please excuse the stage fright. Hi, down there. Just one quick question. I had absolutely no idea of what you were going to expect from this panel. So, how many in here has ever taken a physics class? Just raise your hands. Good, good, good. Thank you. Then at least it won't be total incomprehension here. All right, CosplayTronics, as I chose to name this panel, not this planet. It's going to deal with mechanics, with electronics, and with Mechatronics, which is essentially the combination of electronics and mechanics into one. I'll have to warn you though, this panel will contain physics. If you feel your brain overloading, just lie down, assume fetal position, and think of pink happy unicorns until reality goes away. Yeah. Alright, so let's start off with mechanics. This is the science of how things move. The most central part of it is this equation. It's about force. I bet you all know from Star Wars, you know, you just point at something and it goes up. And to represent force today, we're using Yoda. Yoda can raise an X-wing out of a bog without, you know, straining his eyebrows too much. So the force he uses equals the mass of this X-wing that he's raising, and times the acceleration. Now, to demonstrate this properly, I'm going to need someone from the audience. Hi, would you like to help me for a bit? All right, all you have to do is just stand here. Yes? Okay. Now I'm going to use a force. Excuse me, do you have a mass? No, just... Okay, great, great, great. I'm not going to ask what it is, because that would be rude. All right, so we have an unknown weight. We're going to apply a force, and it's going to accelerate. So I'm just going to give you an even push like this, and an acceleration. That's how it works. If you get this, if you can understand this equation, it's just 3 letters, pretty much. Thank you, by the way. Excellent demonstration there. If you get this equation, you can solve almost any physics problems that reality is going to throw at you. It's so useful, you just have to remember. In the practical unit known as newtons, it's a pretty weird definition, but let's just call it newtons. We can call it Yodas as well, if that's more, if that's what you want to. It's actually been defined as a unit, as he has a force output that could actually drive a small car. But newtons equals the mass in kilograms times the acceleration. Pretty basic. Next up is torque. This is essentially just force multiplied by a distance. It's simply what you apply when you're tightening a bolt, or similar, just turning something. And this comes with the excellent unit Newton meters, just because it's newtons and meters multiplied together. Easy, easy, easy. Also incredibly useful is equilibrium. This is simply how things balance. Like if you want to build a giant hammer and you don't want it to be very front heavy, you can just apply another weight at the other end and you'll look really strong when you're just wielding this hammer around like woo, woo. The thing is, light things have a very low mass, so you can accelerate them really quickly. They don't look heavy. If you want it to seem heavy, all you have to do is accelerate it slower, really make the weight count for it. Even if you're the Hulk, you can't really swing a 40-ton Panzer around your head without losing your footing. So it's kind of boring to be an engineer and look at movies like that, because you spot all those common physics mistakes and you just go, So that about that. Equilibrium, incredibly useful if you're going to build anything that is balanced or anything that has any kind of gearing, or if you're going to build a dragon and don't want to strain your back too much, you can just add a counterweight behind you so you can lift the entire thing without breaking it. It's also how gears and gearing works, but instead of using the length, you simply use the radius of the wheel. Anybody understood that? Raise your hand if you understood it. Yes, yes, I'm doing this right. I'm so proud of you. That was like 10% of the audience. I was expecting 1. Anyway, this is useful if you're going to make anything move faster or slower. Since we'll be talking motos later, it will be very useful for you if you're going to make anything that's actually going to move. That about that. Anything else I want to say about this? Well, what can you use it for? Obviously, you can use it for everything I said, but you can also use it to make some pretty wings, for example. Isn't that beautiful? Just flap up and flap down. I want to see it again. Yeah, just look at it. Ain't it pretty? Okay, let's watch it one more time. And this time, look at what's happening. Look at her right hand. Oh, I didn't really reset there. There we go. Right hand is going down when the wings are raised. So essentially, what the wing structure looks like is 1 going from the back. There we have a person here wearing the wings. And you have the wing panel here with some pretty feathers on it. And from here, you have a string going down there, going down to the right hand, so that when the right hand is extended, the wing raises. Very easy to make. Very, very easy to make. The question is, of course, how long should this piece be? Because that one is going to screw up how the wing looks. You don't want this big poker sticking out of the wing that goes down when the rest of the wing goes up. I'm just going to illustrate that really quickly with this useful piece. There we go. This part here. You'll want to minimize that since it doesn't really appear in elbows. It's so very short. But then you can apply the equation of equilibrium. Since we have... I'm just going to write that down here. There we go. I hope it's not too incomprehensible, my writing. But we have a force, which is the wing pulling down. That's gravitation. And we have a length, which is the length to the center point of the wing, assuming it's got an equal distribution of weight, but it's center of gravity for the wing. And on the other hand, that's the force that goes down times the length. On the other hand, we have the force that we need to apply with a hand times the length that we use on the countermeasure. If we can minimize this, we can use as little movement and as much force as possible, making the movement almost invisible, which means your wings will raise almost magically into the air. Pretty neat. So assuming the wing weighs about 1 kilogram, we'll have 10 newtons here, and since this is a ruler, I can just measure this as 20 centimeters, so you'd have about 2 newton meters, working here, which means we'll have to use about 20 newton meters to work it the other way. If we use 2 centimeters here, 2 centimeters, that's a really short distance, then we'll need to apply 200 newtons by pushing down your hand. And since we know the coefficient of specific gravity, it's 9.81, but for all practical purposes, you can count it as 10, you'll need to push 20 kilograms down to raise a wing such as that. That's how you use the equilibrium equation. And onwards. Mechanical systems. there are lots and lots of useful mechanical systems. I've included a lot in Puff over there, and I can't really give you any guidelines to how you build these. But Legos, constructions, everything, they're all around you. All you have to do is look at your folding chair and take some inspiration from that. There's garden chairs, there's umbrellas, there's these sock dryers. I don't know what they're called in English, actually. But just try to find someone who has already solved your problem. In this business, it's quite often the easiest way to do it. Instead of trying to solve the problem, try to find something that moves just like what you're looking for. And that was just a little bit of inspiration about animatronics and, you know, industrial robots. Let's just skip that, it's boring, and go to electronics. Electronics. How many in here knows how to solder? Yes, a few ones. I'll be setting up my soldering gear in the cosplay nödhjälp over there afterwards, if anybody wants to learn it. This is the hot gluing of electronics. This is what you need. You can twist wires, you can use actual hot glue, I've done that, on your cables to make them stick together, but once you learn this, it is so amazingly easy and useful. If you're going to, I mean, even if it's just LEDs and batteries, just solder it together and you'll be happy for life, because it's going to work at the con. It's not going to break. You're not going to sit there with a mass of cables and electric wires and tape and all that, and nothing works and you're unhappy and all that. Anyway, it's really easy. You take a soldering iron, you heat your components up, you melt some tin on it, done. That easy. With that part, let's go to the physics of electronics. This can be a little bit abstract because you can't really see electrons move around, but I've tried my best to make some analogies. Voltage. You recognize it from batteries. It's the potential of the battery. The pressure of a water column is what I've used to symbolize it. Since you know your ears lock on whatever it's called when you dive down deep, that is because pressure rises. And the higher the pressure is, if you say make a hole in your water tank, you're going to get a small fountain of water. The higher the pressure is behind this, the more water is going to come out. The longer the vannstråle is going to be. Sorry, I just can't find the word. But voltage, that's essentially the height of your dam. The ampere hours is how much water is in the dam. That's how many electrons there is in your battery, shortly. Next is current. This is how much water is passing through your pipe at any given moment. It's the amount of electrons that passes through your electronic circuit. It's measured in ampere, which is named after a guy in the 16th century who invented it. Let's say he did. Next is resistance. And this is how much you restrain your voltage, how much you restrain your amperage. And together, these form Ohm's law. If you, just as with the force equaling mass times acceleration, this is all you need to know for all basic electronics. If you understand this, if you don't have to understand it now, I'm just trying to give you an introduction to it so that when your physics teacher takes it up or when you read it up on Wikipedia, you at least have some basic concept of what this is all about. This works so that the voltage is equal to your current times your resistance. Very easy. It's as if it was defined to be easy. This is very, very useful when you're designing an electric circuit, because you can take a resistor, you can add a battery, and you'll know just from the components what your current is going to be. And the current, that's what's controlling how fast your engine spins or how bright your LED is shining. So that is the basic law for controlling the electronics, for knowing what it all is about. And that brings us to components. I've already mentioned batteries. You sure know them. They come in different voltages, different sizes, all different types of things you put in them to make them work. Basically, this is pretty much just cells of battery that are stacked on top of each other. This is how a 1.5 voltage battery looks like if you open it up and look at it inside. So you take all these tiny little cells and stack them on top of each other until you get 1.5 volts, and that is your battery. But that helps us because that means we can also stack 1.5 volt batteries on top of each other. If we want 3 volts, use 2. If we want 6 volts, use 4, and so on until you reach the megavolt section where you have about 1 kilometer of batteries and you can literally power a death ray for 1.0 second. Sorry? Adjusted? Ah, okay, thank you. It also means that we can put them next to each other. If we use the water analogy again, this means that you're actually adding more water to your dam, meaning the battery life would last longer. If you have only one battery running it, let's say it lasts for 1 hour. If you have 2 batteries in parallel, it will last for 2 hours. If you have 4 batteries, it will last for 4 hours, and so on. And you can make it last forever by using an infinite amount of batteries, of course. Next up is resistors. Resistors are teeny tiny little things that lead electrical current through it. And essentially what they do is they just break up the electrons so they move slower. And this produces heat. So the resistors basically just slow down the current. This is very useful when combining it with LEDs or making circuits that rely on timing between different signals. They can be added just like batteries on top of each other. At that point, they just pretty much add up to a final sum. Just add the resistors together if you put them in a row. That means if you only have one size of resistor, let's say you have 1,000 ohms, that's a pretty usual resistor. You can buy them in big shopping bags and have forever. But that means you can add this into 1,000 ohms or in 2,000 ohms or 3,000 ohms just by adding them on top of each other. If you want less, then you can add them in parallel, because that simply means that you add another channel for the water to flow through. So even though they have the same resistance, you essentially just halve the resistance. So if we take 200 ohm resistors and put them next to each other, just solder them together there and there, lead your current in out from the other, actually producing 100 ohm. Might seem a little bit strange, but by combining this, that parallel and stacking the resistors, you can essentially from only one kind of resistor just produce resistance that you might need. You only need one sort. As long, of course, as you understand this, which I, from your silence, take that you do. Just remember, pink fluffy unicorns, if it gets too much, or just start booing and I'll go on to the more funny parts. Diodes, also a very useful component. This is your one-way entrance. This leads current one way, it can't go back the other way. This can be used to, for example, convert alternating current into direct current through the clever use of a diode bridge. But what we're essentially going to be using is the light-emitting diode, which is much more interesting for you, since you'll be wanting to light up your hair, or your head, or your gas mask, or your portal gun, or your lightsaber, or your Omni tool, or anything else like that. There's also a few special LED kinds, and and products that can be used, like glow specs or the Adafruit electronics. I just brought some to show you here. This is my Space Marine helmet. I don't know if you can see this, but this is essentially a pair of glow specs that is mounted inside the helmets. And there we go. I should have soldered it. These glow specs are actually pretty neat because it's made from plastics with different diffraction index. I'm not going to go into that, but essentially it just bounces light outwards. So the light goes out of the glasses, but not into your eyes, which means you can see out of them even though they're glowing. Pretty neat. Now, where did I put that one? Yes. Yes, LEDs. To hook up an LED, you need to know two things, really. First, the positive and negative. The positive is the long one, because plus, long, and the negative is the small one, the short one. And, well, since it's a diode, you won't get any current if you do this backwards. You can only do it right one way, so try it out and you'll learn it pretty quickly. Specs for, yeah, they've got a forward voltage. You pretty much need to get up to a certain voltage for it to bridge, so to say. That's when the current goes through and you'll get a light. They also have a forward current, which, did I say forward current first? I meant forward voltage. But the forward current, that is going to regulate how much light you get out of it. If you do it too much, the LED is going to just fry and never light up again. I've done that to a few. Don't do it. It's just kind of ruin it. It also has the spec that is called millicandela, which is essentially thousands of the light produced by one candle. It's the intensity of the light. So if you ever go onto eBay and try to find some specs for LEDs, don't buy the ones with 100 millicandela because they're barely going to be visible. They also have a wavelength. I'm going to get to that in just a few seconds. Just going to mention that there are diffused and clear lights for LEDs, just depending on what kind of light you want. Don't buy colored LEDs. They come in wavelengths, which means that essentially you have a number that describes exactly what kind of wavelength the LED is producing. And it only produces one wavelength, which means if someone has colored the LED, they're essentially just putting in another color because that was cheaper and filtering out the wavelengths that you don't want, which means you don't get as much light. So simply buy the ones that has the wavelength you need, and there are plenty of online converters for between nanometers and the NCS scale for colors, or whatever else you can find to match the light shown in Pokemon for your Pikachu suit, or something else like that. All online, Google it. So easy. The LED setup is unusual because LEDs, when powered, don't have any resistance at all. They have infinite resistance one way and no resistance the other way, which means essentially because the voltage equals the current times the resistance, and if the resistance is zero, the current has to be infinite for it to work out, which means if you don't use a resistor, the LED is pretty much going to just empty your battery. That. It's like an open circuit. There are also lots of LED calculators online. I'm not going into that. You just Google it and insert how many milliamperes you want specified on most LEDs. They go by 10 milliampere or something, 20 milliamperes. Input that, input the voltage of your battery, and it will give you the size of the resistor. And since you know exactly how to combine any resistor you'd want now, you can simply puzzle that together and you got a working LED circuit. Switches. It's pretty much just the on-off power button. Install one. You're going to want it because it's such a hassle to uncouple and couple batteries. There are a few different kinds. The kind you use in for example, what's it called? The thing you write on computers. The keyboard. Yes, the keyboard. Thank you. That's a push to close circuit, for example. When you have it pushed, it sends a signal. They're also push to break the circuit, which essentially just breaks the circuit when you push it. But these are very small, very handy. You can hide them in gloves, for example, so just when you touch your fingers together, your LEDs light up, for example. There's also the usual flick and push, and just push it like a ballpoint pen and it's on, or flick the switch. You know it. You've used electronic products. Yeah, all those can be bought at an electronics shop or at Shell Company or in the tiny little electronics. eBay, thank you. eBay also, if you want a pack of 100 switches, whatever you're going to use 100 switches for, but I want to see it. Transistors. This is an incredibly useful tool. It's a little bit more advanced component. You can make radios from it if you're advanced enough. But essentially, this is a water tap. You apply a tiny bit of force to it, or a bit of current, in the case of a transistor, and it opens a circuit, or closes a circuit, depending on the transistor. This can be very useful if you want to control a much stronger current or want to have a signal that you send from a microcircuit or from a button, for example. Combine it with, for example, a capacitor. A capacitor is a reservoir. It's essentially a bin of water that you can just fill, and when you close the circuit, it's going to slowly empty. And combine these two is what I did for this circuit, for example. It is for my frost moon that I'm building. Essentially, you flick on the switch and it fades on. That's because the inherent delay when the capacitor is filled. And when the circuit is then switched off, the circuit breaks and no more electricity is fed into the capacitor. But since the capacitor is still full and hooked up to the transistor keeps the LED circuit, which is just the battery and the LEDs, open for a while the capacitor is slowly emptying through the transistor, which means that the current is slowly being strangled for the LEDs. It just fades off. Essentially, fade on, fade off circuit. Hook it up, pretty easy components, pretty easy to make, just solder it together and you'll amaze people. Because people don't know how to do this. I don't know why. It's so easy, for me at least. Breadboards. I love breadboards. This is essentially your I don't know if you built Legos anytime, but you know these green plates you can have at the bottom that you just build your house upon. This is, you just stick your components into it, stick a few cables in it, and you don't have to solder anything when you're going to test your circuit. It saves so much time. If you learn to solder, you can solder the circuit together, but if it doesn't work, you'll have to unsolder it and retry it and try to find the shorts and all that. In the breadboard, you just move it to another position. It's not even expensive. There's also microcontrollers. I think you should know about them. The Arduino is one of the most famous. There's also Raspberry Pi. If you want to use them, you're going to have to learn a little bit of programming. Is that a question? Okay. Ah, okay. Good for you. You're going to have to learn a little bit of programming to do it. When you do, if you do, you're going to be able to make anything. And I mean it. Literally anything you can think of. This little piece, I mean, it's about the size of this. If you want your LEDs to blink or run through, I mean, like that, or just blink, or have a text message scroll through. You can build that using this. I've made some, I've only used it for, but I'm amazed at the versatility of it. I mean, people have built entire, I've seen this most amazing Lego construction. It's kind of Legoception, because it's essentially a big factory, and you do your input by pushing a few Lego bricks that sends the signal to the Arduino, and it has small robot arms and moves bricks from a magazine and assembles it to a tiny little Lego car according to your specifics. It takes about 15 minutes for it to run through, but it assembles Lego bricks. You just push buttons and it assembles Lego bricks. It's amazing. I could sit and watch it all day. It's on YouTube. Google it. Controls for it. These are pretty much just variation distance. This is the easiest one to pick up. I mean, you can vary voltage and so on, but usually you don't have a fluctuating voltage source. You don't want to, I promise. The potentiometer is the most usual one. This is essentially just a twist, a knob for twisting, and it changes resistance. So, turning a tap and strangling your water hose, for example. That way you can adjust the intensity of your LEDs or how fast a motor goes. I'm sure some of you have already used potentiometers without actually knowing it. When you turn the volume knob on your stereo, it's a potentiometer you're turning. There's switches, of course, I've already covered that. There's the bend sensor, which is essentially a sensor that changes resistance when it bends. So essentially you could just make a glove and have these along the fingers and bend your fingers and something happens. Sound. Sound is also the nice part of electronics. I've brought a few things here that I'd like to show you. And since you now know everything about everything... No, don't tell me you're not working. Yes, yes. Can you hear that? I don't know if you can hear that. I'm just going to put this here. There we go. And there we go. And I'm just going to... No, wait. I got one of these for it. Can I get some sound on this? Oh, there you go. And this essentially works like this. Hear that? Yeah. Essentially, it's a switch that is reacting on movement that sends a signal to a small soundboard, which then plays the appropriate sound. You can twist the knob here if you want different themes here. There's the night. Kinda neat. There's 8-bit hero. Great fun. This is called a Mega Stomp Panic. If you learn if you get through the basics here, you could essentially build one like this. You could get an Arduino and you can find a soundboard and you can essentially hijack a switch like that to react to your movement, and you'd have sound for a costume. Imagine that. I've also brought this little piece of fancy equipment here. Let's just see if I can get this to work. I'll just put it here. Assemble the entire line of electronics. And on switch. No, did I leave it on? Hello, 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 hello. No. Seems I left it on overnight and now it's drained the battery. Too bad! It's a voice changer. It essentially picks up your voice and runs it through a few circuits, and you can just change the pitch by a few button switches. Too bad that didn't work, but we can just go on to the next. That's it for electronics. So let's go on to mechatronics. Now, I want to warn you, mechatronics can do a lot of things, but there are some things it just can't handle. I'm going to need someone to demonstrate something for me. You can? Frida, come here, please. Right. Now, Frida, you're a mechatronic system. Okay. Are you ready? On switched? Yes. Please catch these bananas. Bananas? Exactly. She performed the intended action while I was giving her the wrong information. Give her an applause. No robot today can do that. Not only that, she interpreted complex visual information and coordinated her extremities to actually catch it with timing. That is insane in mechatronic terms. So whatever you do with this, you're never going to get beyond hand power, hand-eye coordination. It's essentially impossible at this level. With that disclaimer, onwards. I'm going to talk a bit about motors, different kinds of motors, servo motors and hydraulics. That's what it will cover. Electric motors. Rotation speed, rotations per minute, usually in 1500s to 3000 is really fast. But since you know gears, you can essentially gear it down to simply produce a lower speed. They also produce a torque, force times the length of arm, remember? So if you put a 1 meter long arm on it, it's going to produce a specific amount of newtons out here. And the torque of the motor, that is that number, the number of newtons. So if you want something to lift a toad that is on a 1 meter stick and the toad weighs 1 kilogram, you're going to need a torque of 1 Newton meter. And it's going to lift the toad, and as the force decreases and the toad descends, it's going to accelerate until the toad is flung into the distance. I couldn't do this experiment on stage because I couldn't find a 1 kilogram toad. Otherwise, I would. It also has a forward voltage and amperage. The forward voltage is pretty much how much batteries you're going to need to make it rotate. The ampere, the current that goes through, how many electrons per second, that is going to adjust the speed. Which means that if you use a potentiometer to adjust the current, you can adjust the speed of how fast the motor is rotating. Pretty neat. You can also hook it up to a battery, just plain and simple, and electric motors are pretty much just magnets in spole, in a coil, that's the word. If you exchange the poles, it's going to turn the other way. Now, what can you use this for? Obviously, you can use it to power a propeller hat, but since we're talking motors, I brought this, my bolt gun from Warhammer 40K. Just gonna find the on switch here. Oh yeah, there. It fires ping pong balls. Now, who can tell me what this looks like inside? There's one at the back. There, please. It does contain motors, since we're talking about it. Yes, at the front row here. Yes? Okay. A fan. No, it's not a fan. It's essentially two motors mounted like this. And then there's a paper pipe right here in the gun. Looks like this. There, gone. Very pretty. And on these motors, there's mounted a wheel. And one wheel rotates this way. The other wheel rotates the other way. Essentially, I've just flipped the switches. So one motor is running one way and one motor is running the other way. And then there's a feeding mechanism and ping pong balls in here. And they are fired out here at killing rates. That is motors. Nothing more fun to show that. Let's go to servo motors. These are the thing. This is what you use to make things move. The motor, it never knows where it is or what it's doing. It's just spinning. The servo motor always knows which way it's pointing. Essentially, it's a small electronic thing with a wheel on top, and it can rotate about 120 degrees, usually used in radio-controlled cars and airplanes and things like that. There's a few different models. I included some pictures here just for your reference if you want to look through this presentation afterwards. They run at either 4.8 or 6 volts, but you can run it at anything between. The thing is, the higher the voltage, the more torque you're going to get out of it, meaning the faster it's going to move, and the more weight it can move. Other than that, it comes with the almost retarded unit kilogram centimeters, which is essentially torque. Newton meters, just in a little bit different way of putting it. Essentially, they're cutting out acceleration, assuming it's 10 for going downwards, and simply says that at 1 centimeter, it can lift this many kilograms. So if it has 4 kilogram centimeters, the servo can lift 4 kilos at a distance of 1 centimeter. Not very much, but it's very useful for airplanes and radio-controlled similar. Now, to control this servo motor, you're going to need something that can send the servo signal. That's what you're seeing down here. It's a pulse. And the distance between the length of the pulse says where the motor should stand. The easiest way to do this is to get a servo tester. It's essentially a potentiometer, a knob that you turn. And the servo simply mimics the turn that you make on the potentiometer. So if you turn it 45 degrees, the servo is going to turn to 45 degrees. If you turn it to 90 degrees, it's going to turn to 90 degrees, and so on. If you want to make more complex stuff than that, you're going to need a microcontroller. There's also radio control systems that you can usually find in airplanes and similar. I've brought one of my own radio systems here. I'm just going to change hats. Let's see if this works. This is my Lich King helmet. As soon as I've gotten over the trauma, Puff the Magic Dragon, I'm going to finish this. So essentially, I've made a glove. No wires, no nothing. And then just push a button and magic. This is a car door controller. It's the kind of thing you use to raise your garage port. And at the back of the helmet, I have just covered in tape now, since it's still at the production state. That's the kind of things you can use. Not very expensive. Bought it from Adafruit. They have a few switches and controls for that you can order online. But essentially, if you can find it and it works, you can use remote control for an old television set or something else like that, just as long as you can figure out how it works. Next up, you can use servos for any number of things, like moving helmet visors, or making your tail wave, or making your ears wave. This is those Neko Mimi ears. But you can, if you learn to use servos, you can use it for horns, or for bunny ears, or for for I don't know, tentacles, whatever you want to make move. You can make it use, this is me by the way, he's the fanboy, but he was a really big fan of Warhammer 40k. This is essentially a pair of gloves with bend sensors on it, coupled to Arduinos, which means that when I move my fingers, these servo arms move. I can give people 6-arm hugs. Yeah, pretty neat. It also makes you very, very claustrophobic, because you can't move your fingers, because your arms are going to be flailing everywhere. Hydraulics. Usually intended for incredibly large forces. Like for, I don't know if you can see it, but this digging machine down there has a smaller tractor down there just by its larva feet there. Yeah, that's a full wheel loader. This is a monster machine. However, they come in much smaller versions as well, like for Legos. Then it's called pneumatics and usually runs on air. You simply pump up air until you have a full balloon or air tank or similar, and with the pressure, you either add air to air before or after the piston, and it will either extend outwards or contract. Very useful if you need linear. Legos, yes, get yourself some Legos. This is the shit for learning mechanics. Actually, if you want to learn how to control things, if you want to build dragons and whatnot, get yourself a kit of Lego Technics just to assemble it and watch it. For I don't know about you, but for engineers, it's an incredible satisfaction to just see things move. Or you could use pneumatics to make extending Wolverine claws, like this. This guy is kind of crazy, but he pretty much welded together a pneumatic backpack that he can fill with air, and then he pushes there, fills air into his rucksack, and then pushes a switch to engage the pistons in his arms, extending the Wolverine claws. I mean, how cool is that? I wish I could weld. Yeah, that's about all the things I was going to go through. Do you have any questions? From your silence, I take it that you either understood everything or nothing. I kind of suspect it was the later part. Yes, Waldo at the front.
Oh.
Good thinking.
Yeah, I didn't see that come, but why didn't you talk about cats?
Why I didn't talk about cats? That's because biology, though it is kind of similar to mechatronics, kind of more complicated than this, so I tried to keep it basic. If you want to find a mechanical system, the best source of inspiration is actually nature. If you can find out how your elbow works, it's essentially an equilibrium system where you apply a force to the front while applying a force through the bone, through the back, and you can start lifting weight and practice creating more and more potential. Get those newtons in your muscles, you know. That's why I didn't talk about cats. It's a fascinating subject, but not for this panel. Maleficent at the front, you have a question. I think it's
Hello?
on.
Okay. What will you build next, oh handsome master of creation?
Why did I? It was 1:30 when I wrote that question yesterday, or well, this morning. I'm going to recover from Puff for a while. Then I'm going to finish the Lich King, and then I'm going to figure out how to make Warbler at home. That's going to be a fascinating subject. I'm just tired of the shenanigans. Then I'm going to figure out how to make a snake body. I mean, essentially put yourself into a suit and, don't know, just flip a switch and go about on a wagon and have a whole tail follow you. That would be awesome. Or something similar. I've been looking at 6-armed aliens and other stuff like that. It's essentially what creativity is going to put me in the direction of. Any other questions? I'm at +4 seconds now, at overtime.
Hello. Do you have any disaster stories of what not to do?
What not to do? Okay, don't make things that shoot people, okay? I've figured out how to make that one fully automatic. You know, with a bag of ping pong balls, you just plug in a leaf blower, and you can pretty much just spray the entire with ping pong balls. Not con-safe. Very much fun, not con-safe. Don't use too much force either. Don't go over 12 volts because reasons. You die if you do it wrong. If you short circuit between one finger and the other, the current is going to go right through your chest. Don't put forks in the socket. Sure, it looks fun, you'll explode, but that's about it. What else not to do? Try to build something with fans, okay? I've done that mistake a few times, not to include fans in big things where you have to use a lot of work to move around in, and you'll essentially be committing suicide through a heat overload. Don't do that. Make things big enough, or make them smaller, actually, because after you've built half a dragon, I mean, where are you going to put it? I can't have it lying on my sofa forever. Lying on my sofa or taking care of the dragon? Oh. All right. Sorry? Ooh, I live in an apartment, so it's kind of just going to block the stairs. Right? Any other questions? If you think of anything later, you can always drop by on Facebook and just drop me a PM. I love answering these kinds of questions, so I'll just, at any point, just ask me anything you wonder about. That's another question. How I would simulate steam. Oh, that's a good one. Essentially, steam is generated by moisture that dissolves from the air at a pressure drop rate, which means that essentially, if I wanted to simulate steam, I'd find a way to very quickly empty the air from wherever I am. And simply all the moisture in the air would coagulate and it would get really foggy really quickly. Steam, instantly. You could also buy smoke on a can and attach it to a servo motor, for example, and at the flick of a switch you could have a small piece, a small can of smoke empty itself in your thigh gloves or in your backpack or something similar. All right, no more questions, then have some Space Marine, and thanks for me. Did you shut this off? Come now, it's almost working. Can you just manually step one ahead? No. Too bad, didn't work. Oh, thank you.
Yet. Am I on? Yes, I am. Ah, cool. Wow, that was so much information. I was so inspired. We haven't had like a panel with physics before, but that's so cool. Take in everything you learn. Next up, in about 6 minutes, we're going to have a panel working in games and SFX with Lisette Stenquist. So just stay tuned and we'll be back cleaning the stage and just stay here.